Welcome to the Cosmic Savannah with Dr. Daniel Cunnama
and Dr. Jacinta Delhaze. Each episode, we'll be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
Right, so today we have a very exciting special episode.
Ooh, welcome to our bonus episode!
Because just this week, on the 10th of April 2019, astronomers released the first ever image of a black hole.
Can we just say that again?
Astronomers released the first ever image of a black hole.
Ooh.
But wait, what? Anyway, we'll try and break it down for you. So today we have two special guests who will be talking to us a little bit about the Event Horizon Telescope and black holes, and what this discovery means and what was our involvement as South Africans and Africans.
Yeah, that's right. So I guess the first place to start is to talk about the telescope that did all of this. It's called the Event Horizon Telescope, or EHT. And to understand what the EHT is, we first have to talk about another acronym, VLBI, which stands for Very Long Baseline Interferometry. And what that means is it's like a normal radio telescope, a radio interferometer, where you have several different antennae, different dishes, and you connect the signal together. You join it together on a correlator, on a big computer, and that produces a very high resolution image. So you can see very small details. Now, the details that we are trying to see when we're looking at individual black holes are really small. So we're looking on about 20 micro-arc-second scales. And to give you an idea of how big that is, a couple of comparisons I've seen in the news and on Twitter recently, if you were in Paris, you would be able to read the print on a newspaper in New York. And there was another one too. If you were in Brussels, you'd be able to see a mustard seed in Washington, D.C.
Yeah, so this very long baseline interferometry combines these telescopes around the world. And in this particular case, the Event Horizon Telescope has combined the 8 telescopes ranging from Hawaii, South America, Spain, and numerous other locations to operate as a single telescope with the aperture of the size of the Earth. And by doing that, we can get this resolution that Jacinta was talking about. And what that means is that if we look in a very particular wavelength, and that's what we've done here, in about a millimeter wavelength, we can actually observe the light around a black hole.
And this has never been done before, right?
No, so the technology required to do this, obviously, firstly you need the individual telescopes to exist and to operate. Then you need to form this consortium and form a plan and organize these operations, and so that everybody can do an observation at the exact same time. Then you have to choose your target, try and observe it, hope the weather's good at 8 different locations around the world, and then take an observation, do a very large amount of data reduction, and hope that what comes out of it is what you kind of expect when you model the light around a black hole.
Yeah, and the data was far too much to send via the internet, so it actually had to go onto enormous hard disks and physically taken to the processing centers in, I think it was Boston and Bonn.
Yeah. So shipping hard drives around on airplanes with this incredibly interesting data. So the observation in particular that we're talking about now, this black hole at the center of M87. M87 is a galaxy fairly near to us, 55 million light years away, so in our galactic neighborhood. And the black hole sitting at the center is 6.5 billion times the mass of our sun. So it's a very, very big black hole.
6.5
billion.
Billion. That's pretty big.
And it's 1,000 times bigger than the black hole at the center of our galaxy, the Milky Way, which is also pretty big. So it's a very, very big black hole. And that was why it was one of the targets, right? It was, fairly nearby a very, very big black hole. So, we would expect a fairly large, relatively large angle in the sky. And yeah, the astronomers with the EHT have basically combined forces to make this observation and release this image.
Yeah, and I guess, so if you've heard our previous episode 4, we spoke to a few radio astronomers about looking at galaxies that have supermassive black holes in them and what kind of intense energy processes can be released as a result of this. Now, these supermassive black holes are not doing something as intense as that, but there is stuff orbiting them, gas and dust, and orbiting close to this black hole, creating a plasma, heating up to enormous temperatures, and glowing, basically.
Yeah, and then the light that comes off this accretion disk, so it's a disk of material which is slowly falling into the black hole. The light that comes off this gets bent quite violently by the mass of that black hole. So space and time is heavily distorted by something of this mass, which means that the light behaves in very predictable, with relativity, but quite weird ways. And that's, what we essentially have observed now is how this light has bent around this black hole, and been beamed towards us in this very neat little ring, showing us the matter residing around this black hole in a very distant galaxy.
Yeah, and I mean, I'm sure by now you've probably seen a picture of it. It's splashed all over the news. But if you haven't, it'll be on our website. You can have a look at that picture, and I think it looks like the Eye of Sauron.
Yeah, there's been a lot of social media attention around it, and a lot of memes and things popping up.
I've really been enjoying them.
But to give us more of an idea of what went into this observation, we're now joined via Skype from Brussels by Dr Roger Deane, who is an associate professor at the University of Pretoria in South Africa, and his team was involved in some of the background work of this observation.
Yeah, we'll just warn our listeners that this conversation was via Skype because Roger is in Brussels for the big press conference and to make the announcement. So the quality of the recording isn't super high, but we know our listeners are all very intelligent, switched on people, and I'm sure you'll all be able to fill in the blank words when it cuts out.
That's a nice little game for you.
Yep. Hello, Roger. Can you hear us?
I can't actually. Sorry, I'm in Brussels.
Yeah.
So I hope this works out.
What are you doing in Brussels, Roger?
So I was really lucky to come to the announcement of the event, the first imaging results of the Event Horizon Telescope yesterday, for all the world to see. So I went to the European Commission, where one of 6 press conferences was held, and announced the first image of a black hole.
Yeah, it was very, very exciting. We were following on social media and following the press conference live. And I think there was a lot of excitement both in the scientific community as well as the public from this. I think everybody's social media feeds are full of images of the supermassive black hole. Can we start with what exactly is the Event Horizon Telescope?
Sure. So the Event Horizon Telescope is what we call a very long baseline interferometer. That's a mouthful, so I'll break it down. What we do is we have radio antennas spread on continental and indeed planet-sized distances apart from one another. And then we bring those signals together and combine them with very, very high precision. So the EHT is a VLBI array, uses that same technique of synthesizing an Earth-sized telescope, but it's special from other Earth-sized, other VLBI arrays So the wavelength of light that it observes, if you looked at two consecutive peaks, the distance between those two peaks would be 1 millimeter. But to do this, it has the antennas on very, very high and dry sites. They need to be up on 5,000 meter volcanoes in Hawaii, down to the South Pole where it's very, very dry. And the reason for that is the atmosphere basically absorbs these frequencies.
That's great. And Roger, what did we actually detect? What did we look at with the EHT?
Well, to summarize, a ring of fire. The great word Johnny Cash. But the image that was made was a complete ring, which is basically what we call the shadow of the black hole. What we were seeing is light in the immediate vicinity of that boundary layer, which defines the point of no return when you enter the black hole and sort of exit our universe. There's a sharp feature at this boundary point. So there is a point at which light disappears from the universe, if you will, or at least from our view of it, and that which does come to our telescope in our eyes. And that is a sharp feature known as the black hole shadow.
And which black hole did we look at?
So on cosmic scales, this is a fairly nearby giant, what we call elliptical, about 55 million light years away. And essentially at the center of this gargantuan galaxy lies a very, very massive black hole, 6.5 billion times the mass of us. And that was the image that we unveiled yesterday.
So, Roger, why this galaxy? I mean, I think most people would expect that we would try and go for the supermassive black hole at the center of our own galaxy, the Milky Way. Why was this the first one?
Yeah, that's a really good question. Why those two targets are best candidates and our primary targets as the EHT consortium. The shadow size that I'm describing, that sharp feature, the ring of fire, scales with the mass of the black hole. But obviously the more distant the black hole, the smaller it appears. So if you combine the distance, those two targets would have the largest apparent size of their shadow on the sky. So that's why those are the two priorities. So both of these are predicted to have a shadow size about the same size. They are very different black holes, though. They are 1,000 times. So our Milky Way, the more nearby Milky Way black hole is about 1,000 times closer than M87. Now, there's a bit of a complication to the observations of the black hole at the center of our galaxy in that it's 1,000 times less massive than the black hole M87 that we revealed yesterday. So that means it's also 1,000 times faster. And by that, essentially there is variability of the emission. It changes on timescales of minutes. That presents a challenge to our calibration techniques. So it was a lot easier for that reason. And then a second reason is that we lie in that thin disk, and in that disk there are a lot of free electrons, which actually distort our view of even at these high frequencies. So it could that process could actually erase the signature as well. So it's a much faster black hole, if you will, at the center of our galaxy, and we have this added complication of living in the galaxy, which make it a harder target. But we've set our sights on that, and data processing is happening as we speak.
So last year with the Meerkat telescope, we observed the center of our Milky Way, and that was in a slightly different wavelength. How is this different, and I mean, how are those related?
Yeah, also a great question. So the beautiful image that was unveiled by Meerkat at the inauguration last year basically shows very energetic phenomena in the galactic center, in that region. The EHT observes that wavelengths of light, as I said, that are 1 millimeter apart between two consecutive peaks, which is about a factor of 100 smaller than the Meerkat image that you saw last year. So it is essentially of one of the pixels right at the center of that image. But there's another factor at play. Even if you had the sharpness of view to see, the actual hot plasma that lies at the center of our galaxy would be opaque to Meerkat. So you really have to go to these high frequencies to be able to actually peer through the gas plasma to be able to see this.
So in terms of coordinating between 8 telescopes across many continents around the world, how do you guys arrange for such an observation? I mean, do you have to wait for a particular date and time?
Yeah, it's a really interesting mode of operation. So firstly, you have to coordinate that you get a block booking, if you will, of all these independent observatories, which includes something like ALMA, which is of the most valued time in the millimeter astronomy. And the way it works is basically every year's campaign gets 5 nights of observing, but it's awarded in a 2-week window. And because we're so critically dependent on good weather on most of the sites, we have an EHT team at every single one of these sites, including the South Pole. And there is a go, no-go decision at the start of every new day based on weather predictions that we have from purpose-built software that we use, which incidentally actually goes into our simulations for later on. So it's 5 nights carefully coordinated, but only decided on the day in a 2-week period around late March, early April of every year.
So we're going to have to wait for another year before another attempt can be made, say, at the Sagittarius A-star?
Well, not quite, because we have data in the can. Because the Event Horizon Telescope Consortium had to basically create new techniques for the actual calibration, imaging, and then B, the analysis, because it's all new. It's been a feverish period of activity within the consortium to get this all right. But things will become a bit easier now that all this work's been done, and data will come, and results will be announced more frequently. But essentially, we still have 2017 data from Sag A star. Yesterday's results on M87 were from the 2017 run as well. We then have 2018 data on both those targets as well. So you might not have to wait as long as a year.
Wonderful.
What was your involvement in this discovery and you and your team at the University of Pretoria?
Right. So the University of Pretoria's role was to create a highly realistic simulation of this Earth-sized array. We did this because we want to understand its limits. We want to understand the extent to which we can actually infer the presence of black hole shadows in the data. This folds in all the complexities and imperfections and corruptions that might come from the engineering of the instrument, the synchronization of the different data streams, and of course the weather that's present above each site, which can erase the signature of a black hole shadow entirely.
So just to explain to the listeners, this simulation, you're basically putting in test information for all of these situations and then seeing how the telescope should respond given those conditions.
Yes, because a radio interferometer, that this instrument where we combine the signals from independent antennas, just like the way that Meerkat works, is it's not a point-and-shoot digital camera. There is quite a complex process of converting voltages into actual images, especially so when you've got antennas spread across the Earth. It exacerbates the problem quite a bit. But essentially, we can take a prediction of what the shadow might look like, and then pass it through in a way that it would mimic the real data, and we can understand the effects of the from the photons hitting the antenna through to the final data analysis. We can understand how our instrumental imperfections and weather are actually impacting those signals.
So there was a lot of excitement and talk when the movie Interstellar came out about that simulation of what we should see, what a black hole should look like. And that was, at the time, touted to be one of the most accurate simulations. That information, I mean, is that useful to you? Are you using those sorts of simulations to feed into your things?
No, the black hole, the Event Horizon Telescope Consortium has developed, I think, what was definitely the largest suite of black hole simulations. That's not my part of the work. That is, theory and general relativity. People working very carefully and figuring out how light behaves in different spacetimes and how the thermodynamics of the gas behaves. But the Event Horizon Telescope developed its own huge suite of these, perhaps not as quite high resolution as the single black hole in Interstellar, but the purpose here was to actually understand the physics. And what you might remember was that in the interstellar black hole, Christopher Nolan decided that there was a certain observational characteristic of the black hole shadow that might be too much for the public to grasp, and that was the fact that the light travels obviously quite close to the speed of light in the immediate vicinity of the shadow. So on one side of the shadow, it's actually brightened, and on the other shadow, it's slightly dimmed. Christopher Nolan removed that aspect of the simulation. He made an executive decision. But in the real image that was unveiled yesterday, you can actually see a difference in the brightness of the ring on one side versus the other. If you have the image in front of you, you'll see the bottom is a lot brighter compared to the top. And that is reflective, we have argued, of this gas that is orbiting the black hole at very, very high velocity, quite close to the speed of light, or at least comparable to the speed of light. And therefore, there is this dimming and brightening effect.
So basically, the black hole and all of the matter around it is spinning very, very rapidly on in the sort of top to bottom axis as we look at the picture.
Well, we know the plasma is spinning fairly rapidly. We don't know for sure about the spin of the black hole, but we could put some constraints on the spin of the black hole. To first order, the dominant effect is actually the mass of the black hole. About a 10% effect is the spin of the black hole. So as we improve the image, we'll be able to make better constraints on how fast the black hole is actually spinning. But we can use independent information on that spin, and we think this is a fairly highly spinning black hole, which is consistent with expectations.
Well, thanks very much for speaking with us, Roger. We'll let you go because we know you're extremely busy and everyone's trying to clamour for an interview with you. So enjoy Brussels, and thanks again.
Yeah, I hope you get some rest and also a bit of a celebration.
Thanks very much, guys. Great to talk to you, and yeah, love your work. Keep going on.
Okay, so that was really exciting. I'm really glad Roger managed to find some time to talk with us. He's been extremely busy, as you can probably imagine. Yeah, I guess so much of that was really exciting. I really liked also hearing about Interstellar and the simulations, and how it's related to black holes and the work that they're doing. I think it's a cool little fact that the simulations in Interstellar were made by a real astrophysicist, Kip Thorne, and his research team. And Kip Thorne later went on to win the Nobel Prize in Physics in 2017 on something different, the discovery of gravitational waves, but also something else that proves Einstein's theories.
Yeah, so not just any physicist doing these calculations, a Nobel Prize winning one. So I think we can trust the simulations in Interstellar with some artistic license, but taken by Christopher Nolan. So what next for the EHT? It was very exciting to hear Roger say that they have data in the bag for Sagittarius A star, which is the black hole at the center of our Milky Way, because while it's a lot smaller than this black hole we've just observed, it's much nearer. So we may see something quite different, moves across the sky very quickly. So it's a completely different challenge to try and observe.
It's 1,000 times smaller, faster, and closer than the black hole in M87. But I've heard it also referred to as like taking a picture of a small toddler that's racing around the house for 8 hours. Quite hard to capture.
Yeah, and in order to do that, the EHT isn't going to be resting on its laurels. They're in the process of incorporating other telescopes into the network so that they can improve their resolution. And there are currently plans afoot to build one of these stations on the African continent in Namibia. And fortunately, we recently spoke to Dr. Rhodri Evans, who was in Cape Town for the formation of the African Astronomical Society, and he spoke to Jacinta about these plans and the incorporation of a telescope in Namibia into the EHT in the future.
Yeah, I just happened to speak to Rodri a couple of weeks ago, and this was, of course, before the announcement, but it was well timed. Obviously, we didn't yet know what was about to be announced, but I think it's super relevant because if we can get this telescope in Namibia, then that's going to dramatically improve the angular resolution of the EHT and maybe give us a better shot at looking at Sagittarius A star, and also exciting that some of the data is already in the bag. Yeah. You heard it here first, folks. Okay, let's hear from Rodri. Hi, we're chatting to Rodri Evans, who works at the University of Namibia. Welcome, Rodri.
Thank you very much.
Can you tell us who you are?
Yes, my name is Rodri Evans. I'm originally from Wales. I'm a senior lecturer at the University of Namibia based on the main campus in Windhoek. And prior to moving to Namibia, I was working at Cardiff University. And prior to that, spent 9 years working in the United States. So sort of typical academic. I've worked in lots of different places. I'm hoping Namibia will be my last stop, although you never know.
How do you find living in Namibia? What's it like?
It's, well, I couldn't have picked a country that's more different from Wales. It's a very dry, desert-like climate in Namibia, and that's actually why the project that I'm working on will be based there. But I find it fascinating because it's so different to what I'm used to. And one of the other things I like about the country is there's only 2 million people who live in the country, even though it's more than 3 times larger than the UK, which has 65 million people. So I enjoy the lack of people and the wide open spaces.
Great. And now you're working on something called the AMT, the Africa Millimeter Telescope. Can you tell us more about what that project is?
Yes, correct. So because Namibia is such a dry country, it's actually ideal for doing a type of astronomy called millimeter wave astronomy. So millimeter wave astronomy, as the name implies, uses electromagnetic waves, which have a wavelength of about a millimeter. And that kind of radiation gets absorbed by water vapor. So you can only do it in very dry places. So, for example, in Europe, it's only really in southern Spain that you can do millimeter wave astronomy. And Namibia is the driest country in sub-Saharan Africa. And we have a mountain called Mount Gamsberg, which is about 3 hours southwest of the capital Windhoek, which is at an altitude of just under 2,400 meters and is extremely dry. So the plan is to put this millimeter wave telescope on Mount Gamsberg, and when it's there, it'll be Africa's first millimeter wave telescope. So the opportunity to be involved in something that was going to be the first on the continent is what attracted me to Namibia.
That's really fantastic, really exciting for Namibia and for Africa. So what will this telescope do?
Well, the telescope will do lots of things, but the main science that it's been sold on is to be part of something called the Event Horizon Telescope. And this is a network of telescopes that are attempting to image the black hole at the center of our Milky Way galaxy. So we now know that there is a black hole at the center of our Milky Way galaxy. The evidence is overwhelming, but as some of the listeners may know, you can't actually see a black hole directly by the very nature that not even light can escape. But what you can do is see the environment around the black hole where the material is falling into the black hole. And the point of sort of no return for a black hole, where once the material crosses it, you'll never see anything from that material, is called the event horizon. And if you calculate the size of the event horizon for the black hole at the center of our Milky Way galaxy, it has it subtends a tiny angle on the sky. It's 10 millionths of an arc second. And there are 3,600 arc seconds in 1 degree. And as people know, 360 degrees in a circle. So it's an absolutely minuscule angle.
Absolutely tiny.
And the only way that we currently have to observe such a tiny angle is to link up telescopes in different parts of the world, a process which we call very long baseline interferometry. And although that's been done at radio wavelengths for decades, actually, if you were to use radio wavelengths, the Earth isn't big enough to be able to image such a small angle, but millimeter waves are at that sweet spot where you can do VLBI. but it's short enough that the Earth is a big enough baseline. So we'll be joining part of an already existing network called the Event Horizon Telescope. The other telescopes are in places like Chile, North America, Hawaii, Greenland, Mexico. But there, South Pole, there's one at the South Pole as well. But there's nothing in Africa. And actually having a telescope in Africa will help improve the images that we can obtain with this network of telescopes. So that's the plan, to put this telescope, 15-meter dish on Mount Gamsberg in Namibia.
Right, so you're putting a telescope on a flat mountaintop in Namibia, and it's going to be connected with other telescopes all around the world, and the goal of that is to image the event horizon of a black hole.
Exactly. So the imaging campaigns, which there was one in 2017, for example, another one last year. They happen in March and April because, as I mentioned earlier, you need extremely dry conditions to do millimeter wave astronomy. And, for example, the dry season in places like the desert southwest of the United States and Mexico is in the March-April time of the year. So that's when the observing campaigns happen. So we will join that network when our telescope is ready in hopefully 2021 or 2022. And as I say, because of the position of our telescope and the fact that it'll be able to link up and see, observe the same object simultaneously with telescopes in the Western Hemisphere, we will improve the resolution of the images that the network of telescopes are able to get.
That's amazing. So can you tell me more about this project to image the event horizon? I've heard it described before as imaging the shadow of a black hole. Is that the same project?
Yes, exactly. So as I mentioned earlier, you can define the event horizon as the point of no return. Once an object crosses that, you won't see any radiation coming from it. So in effect, we're observing that the shadow of the black hole, the material that is just outside of the event horizon that is swirling into the black hole. And given the mass of our black hole at the center of the Milky Way galaxy, which is about 4 million times the mass of our sun, you can work out just from basic physics what size that would mean. And then given our distance from the center of Milky Way, you can work out that it would subtend an angle of 10 millionths of an arcsecond, 10 micro-arcseconds.
Amazing. Roughly. So what do we expect it to look like?
That's a very good question. Actually, my understanding is that the movie Interstellar had a lot of good simulations of what light around a black hole looks like.
It did. I remember that movie.
So probably the best thing is for listeners to rent Interstellar and have a look at the kind of effects that light that a black hole has on light. But basically, we're expecting to see a sort of curve of light as light is distorted by the gravitational effects of the black hole. So Einstein showed back in the early 1900s that gravity will actually bend light. So the light that we'll get from the vicinity of the black hole will be highly distorted by the gravitational effects of the black hole, where of course the gravitational field is extremely strong. But simulations show that by adding the AMT to the network of telescopes, we will significantly improve the image that we see. So we'll be part of a not quite worldwide network, a sort of Western Hemisphere network of telescopes trying to observe this fascinating object at the center of our galaxy.
Yeah, really amazing. So this is in our galaxy, inside the Milky Way, and you said that there's some stuff falling into it, and that's what we're trying to see. Are we in any danger from this black hole?
We're not in any danger from this black hole, and interestingly, it's a question I ask my students. If we were to replace our sun by a black hole with the same mass as our sun, how would it affect the Earth? And the answer is it wouldn't. Apart from the fact that we wouldn't have the heat and the light coming from the sun, our orbit would remain exactly the same. So you actually have to be very close to a black hole to be affected by it and to be sucked into it, to sort of use the popular idea. So it's only material right towards the center of our Milky Way galaxy which has been sucked into the black hole, and certainly the orbit of our sun is completely unaffected by the fact that it's a black hole rather than 4 million stellar objects, the mass of the sun that's at the center.
And how did it get to be so huge? How did it get to be the mass of 4 million suns?
we don't know the answer to that question. So the evidence that we have a black hole at the center of our Milky Way galaxy, there was a very compact object first observed in 1974. And then by the 1980s, a couple of teams, one in the United States at UCLA, University of California, Los Angeles, and the other team based in Germany at one of the Max Planck Institutes. They've been studying the motions of stars for more than 30 years now. And so that's how we know that the central object has this mass of about 4 million times the mass of the sun. It's pretty well determined by the two teams independently. What we don't know is how the supermassive black hole formed. And in the last 15 or so years, the Hubble Space Telescope has discovered that every galaxy that we look at has a supermassive black hole at its center, not just our Milky Way galaxy, but every galaxy. And intriguingly, it seems that the total mass of a galaxy is related quite closely to the mass of the central black hole. There's a correlation between them, and that we do not understand either. So it seems that supermassive black holes play a central role in the formation of galaxies, but quite what that role is not something we know the answer to yet. But certainly being able to essentially directly image the black hole for the first time is quite an important bit of a step in understanding the role of these black holes in our galaxy's evolution and hopefully in the evolution of all galaxies.
So that's some amazing science. Is the AMT going to do any other types of science?
Yeah, so because the observing campaign of the Event Horizon Telescope is only in the March-April, that of course leaves most of the year when it's not going to be doing that particular project. So one of the things that makes the project so interesting to me is that we will have, essentially 10 months of the year when we can do other science with the telescope. So, for example, we're hoping to do a survey of the southern sky at millimeter wavelengths, which really hasn't been done since the telescope that we're going to use was decommissioned. So we're actually going to use an already existing telescope. It's called the Swedish ESO submillimeter telescope, CEST. It went into operation in 1987 and then was decommissioned in 2003. So really since 2003, there hasn't been a telescope doing large-scale surveys of the southern skies. And of course, technology has moved on since then in terms of detector technology, receiver technology. So we're planning to do various observing campaigns, including a large-scale survey of the southern skies, a survey of the Milky Way galaxy, looking at, in particular, the astrochemistry of the Milky Way, the various combinations of different molecules and elements in the Milky Way galaxy, and looking at active galactic nuclei. So these are other signatures of black holes in other galaxies. When we look at some galaxies, we see that the nucleus of the galaxies is particularly active, and that's due to the effects of the central black hole. So we're planning to observe some of these active galactic nuclei beyond our own Milky Way galaxy as well. So there's lots of science that we'll be able to fill the rest of the year with. Now, the driest times of the year are June, July, August. So that's when we'd expect to get the best data. But that doesn't mean we can't be making observations at other times of the year. It's just that we will be more limited in the sensitivity at other times of the year because the atmosphere isn't quite as dry as in the May, June, July, August period.
Great. And you mentioned that the actual telescope that's going on the top of Mount Gamsberg is CEST, the Swedish ESO millimeter telescope. Now, I think you said that's currently in Chile.
Right. So the telescope was put at La Silla in Chile back in 1987. It was operated for some 16 years and then decommissioned in 2003. So it's still sitting there in Chile, and we will dismantle it, take it down bit by bit, ship it initially actually to France to have some repairs, because as it's been sitting idle for the last 16 years, there are a couple of panels that are slightly rusted, need repairing, but actually very, very little. We've done a thorough test of the telescope and everything is fine apart from just needing to replace a couple of the panels. And then once it's been repaired in France, we will ship it down to Namibia and start taking it up the mountain. Now, the mountain, as I mentioned earlier, is at an altitude of nearly 2,400 meters, and it sits about 600 meters higher than the surrounding plain. And the road up to the top of the mountain is extremely precarious, so we're going to have to improve that road. There's no way we can take the parts of the telescope up to the top of the mountain without improving the road. So that's part of the project, will be in improving the road. But it's the top of the mountain. It's often referred to as Namibia's Table Mountain. It has a completely flat top. About 600 meters by maybe 200 meters. So there's lots of room on the top for other telescopes as well. It's an almost undeveloped site at the moment, even though way back in the 1960s, the European Southern Observatory considered it as a place to put the telescopes that ultimately went to Chile. And it was reconsidered again in the 90s when ESO was trying to negotiate, I guess, the site for what became the Very Large Telescope, which was put in a different place in Chile. And maybe as part of the negotiations, they did another site test of Mount Gamsberg just to show that Mount Gamsberg was just as good. And all the tests that have been done on how good an observing site Mount Gamsberg is have shown that it's just as good as Chile. So, my hope is beyond the AMT that Mount Gamsberg can become another site in the Southern Hemisphere for telescopes. At the moment, there's nothing on the top apart from a German amateur telescope. But in 20, 30 years' time, it could be a major observatory like Mauna Kea or some of the sites in Chile.
Wow, that's incredible. So, I mean, it's great that we're recycling this telescope, that it gets a whole new life to do something brand new, and that, Mother Nature has given us this big mountain that's got a completely flat top.
Yep.
And you showed me a picture of that earlier, and it's incredibly, unbelievably flat at the top of this. And we're going to use it to look at the supermassive black hole at the center of the Milky Way.
Absolutely.
That's an incredible story.
Yeah. And Namibia, because of its extremely dry climate and very low population density, has the potential to be one of the major observing places in the world. And for various reasons, it hasn't developed in the last 30, 40 years to be competing with Chile and Hawaii as examples. But there's no reason why that can't happen in the future. It's just a question of developing the infrastructure for the mountain and getting the government on our side for them to see the potential for Namibia of having these telescopes in the country, rather than looking upon it as a negative thing, which, initially most people do. Change is always a bit scary, to get them to realize the huge potential, not just in terms of revenue, but in terms of jobs for local people. I was just chatting in the last couple of weeks to someone who graduated in physics from the University of Namibia, and she's currently teaching, and she said, well, outside of teaching, there aren't any jobs for physicists in Namibia, which, although it's not strictly true, is truer than it should be. And by developing these kinds of facilities, there will be far more job opportunities for people trained in STEM subjects than there currently is.
Wonderful. Well, I mean, we're all wishing you well. We're all cheering for you in Namibia and for the AMT. Is there anything else you'd like to talk about today?
Well, just the fact that, I'm here for a couple of days in Cape Town, seeing all the different projects that are going on in Africa in astronomy. And it really is quite inspiring, because as someone who up until 2 years ago had only ever worked in Europe and North America, it's just great for me to see that there is a lot going on in Africa in astronomy, and certainly Africa needs to do a better job of advertising what it's doing to the rest of the world. But this meeting and the beginning of the Africa Astronomy Society will, it's a start of putting Africa on the world map as far as astronomy is concerned, which it certainly has the potential to be as big a contributor to world astronomy as some of the other better known continents.
And hopefully this podcast will help as well.
Yes, let's hope so, yes.
Thank you very much for speaking with us today, Rodri.
You're welcome. Thank you very much.
Well, it's been a big 24 hours for all of us at the time of recording.
Yeah, it's been very exciting. These astronomical discoveries seem to happen more and more these days. Not a month goes by, it feels like, when something major for the first time gets announced or released.
Or at least not a year until something really major gets announced.
It's very exciting times to live in, and exciting times to be involved in astronomy and astrophysics. And great to hear how Africa is getting involved in some of these project. I think that the incorporation of a telescope in Namibia will greatly improve the resolution of this telescope, the EHT, because at the moment there's nothing on the African continent, and it's a big empty patch in terms of the footprint of that telescope.
Yeah, and as Rodri said, Namibia is perfect because it's really dry, and you need very dry atmosphere in order to do these particular observations. And it also has currently a low population density, which makes it, again, perfect for these kind of observations. So hopefully Mount Gamsberg it is.
Yeah, and then hopefully we'll be involved in improvements in these observations and maybe future observations of other black holes and other galaxies.
Yeah, exactly. I wonder what else we can find, what else we can look at.
I mean, that's the astronomer's motto, isn't it?
Yeah.
Like, make a big discovery. What else can we find?
What next? The very next day. What now?
Absolutely. Well, yeah, I mean, a very exciting special episode. Thank you very much for joining us, and we hope you learned a thing or two. And please join us again soon.
As always, you can follow us on Twitter, Facebook, and our website, thecosmicsavannah.com. And that's where we'll have links related to today's episode.
Yeah. Special thanks today to Associate Professor Roger Deane for joining us via Skype from Brussels, and Dr. Rhodri Evans.
Thanks to Mark Olnut for music production, Yanis Brink for the astrophotography, and Lana Serai for graphic design used to create the podcast art.
The Cosmic Savannah was created with the support of the South African National Research Foundation and the South African Astronomical Observatory.
If you enjoyed this episode, please tell a friend and help us by subscribing on iTunes, Spotify, or wherever you get your podcasts, and leaving us a review.
And we'll speak to you next time on the Cosmic Savannah.